what we can do is we can work together to review this content that we just saw on the 3 slides. So basically, if we look at the NMOS and PMOS, what we mostly interested, in fact, in this class is in the saturation region. But sometimes we don't know whether they're in saturation or triode, so sometimes we have to do try and error. So ideally, we would have to know in the 2 modes, the equations for the 2 modes. So for NMOS, for it to conduct, so VGS has to be larger than VTN, and for PMOS, VSG has to be larger than, let's say, larger than VTP absolute value. And then for the saturation region, that's where we're most interested, is VDS has to be larger than VGS minus VTN, or, well, you can write also VOV equal to VGS minus VTN. And the same thing here, you can write VOV equal to VSG minus VTP absolute value. And for that condition, for that saturation, it's the same thing, but it's VSD has to be larger than VOV. And the equation for that ID is equal to 1/2 K N prime W over L times VOV squared. And same thing here for the ID is equal to 1/2 AP prime W over L VOV squared. If we consider the imperfect condition, then we can write ID as 1/2 Kn prime W over L VOV squared plus VDS over RO. And for that equation, ID is equal to 1/2 Kp squared, Kp prime W over L VOV squared plus VSD over RO. That's the imperfect condition. And in triode mode, we know that VDS must be less than VOV. Same thing here is VSD has to be less than VOV. Here we always use this parenthesis, and the current is going to be Kn prime W over L parenthesis VGS minus VTN squared minus not squared times VDS minus 1/2 VDS squared. And for PMOS, we have ID equal to Kn prime W over L times, and here is VSG minus VTP times VSD minus 1/2 VSD squared. So that's the basic equations. I just want to probably draw also the symbol for us to easily to relate to. That's NMOS. That's the equivalent circuit. It's going to be look like in this. And for PMOS, the equivalent circuit is very similar. It's going to be, and this represents the saturation mode. Okay, VSG is input, and VSD is output, and it's ID RO. So ID RO, VDS is output, and VG is input for the NMOS, and for the PMOS, and for the NMOS. Okay, so this is a quick summary. So now we're going to get into the DC operations. For DC operations, really, we just need to often to design the circuit so that it will give us the correct values that we want. So we're going to start with example 5.3, and we'll go through some exercises and maybe some homeworks. So at the points that we might get into some less difficult problems, and sometimes maybe a little bit more difficult problems that we're going to do. In this problem, we observe what was given. Well, what they wanted to see, they want to design RD and RS. So those two values are not given. But what they wanted is ID is 0.2 milliamps, and VD is 0.2 volts. And what else was given? The VT was given 0.5. The Kn prime is given 400 micro, which is going to be 0.4 milli. And L and W is given. So L is 0.5, W is 15. So W over L is 15 over 0.5 is 30. So those are the parameters given. Lemon is also given was 0. It didn't say whether this problem is in saturation or is it in triode. From the circuit, we wouldn't be able to know. We wouldn't be able to know. At least from first glance, we wouldn't be able to know. So in order to identify whether it's in saturation or whether it's in the triode mode, we would have to basically employ the equations and find out whether our assumption is correct. So let's go. Well, before we get into that, we want to write again those equations. So in triode mode, we want to write ID equal to K and prime W over L times VGS minus VTN VDS minus 1/2 VDS squared. If it's in saturation, we write ID is equal to Kn VGS minus VTN squared. So those are the two very dramatic equations that we need to write. So we can start by examining the circuit. So if you look at the circuit, VD is given. So if I redraw the circuit here, just for our reference, it's 1 volt, 1 volt. VD is 1 volt, VDD is 1 volt, and VD is given at 0.2. So that's 0.2 volts. But VG is actually grounded. So that's important because VSS is minus 1 volt, and then probably later on we also need to find VS, and this VD is given at 0.2 volts. So because voltage is given, we know that current ID is going to be VDD minus VD. That's the voltage drop on the resistor RD, right? So therefore, our RD will be equivalent to VDD minus VD divided by ID. That gives you 1 minus 0.2 divided by 0.2. That gives you 0.8. So that gives you 4 kilo ohms. We have now found RD. The next step is to find RS. But apparently, to find RS, we have to find RS. We need to find VS. So if we can find VS, the RS will be VS minus 1 divided by ID, which is VS plus 1 divided by ID. ID is given is 0.2, so we can replace ID with 0.2. So we need to find VS. In order to find VS, we can go back to those equations where we assume either in saturation or triode. But since the triode mode equation is more difficult, more complex, most of the time we start by assuming in saturation mode. So if we assume in saturation mode, we can write ID equal to 1/2 K W over L times V over V squared. So ID is given. ID is given. Basically, what you get from here is ID is given at 0.2 milli equal to 1/2. K is given at 400 is 0.4, so times 0.4. And WOL was given was 30, so VOV squared. So we can see that VOV will be equal to, when you take a square root, you get positive and negative value, but for MOS, it's always positive, so we'll neglect the negative value. So it's going to be 0.4 cancel. Let's see, we got 0.2, so 0.2, then 0.2 and 0.2 cancel. So we basically is going to be 1/30. So it's 1/30, so 0.03. So we got the number to be, which is 0.18. Yeah, 0.18. So if you don't trust me, we can always go to here. We can say, okay, so I need to get the scientific calculator. Huh? No, this calculator doesn't work. Excuse me. Okay, so VOV is 0.8, but we know VOV is what? The VGS minus VTN, right? So from this equation, we can know that VGS is equal to VOV plus VTN. And VOV now is 0.8, VTN is 0.5, I believe. Yeah, 0.5. So it gives you 0.68 volts is VGS. And VG is what? VGS is equal to VG minus VS. But VG is 0. So minus VS is equal to 0.68 volts. So therefore, VS is equal to minus 0.68 volts. Okay. So if VS is minus 0.68, now we can plug in this equation. Early on, we have RS equal to VS plus 1 divided by 0.2. So VS minus 0.68 plus 1 divided by 0.2. That's 0.32 divided by 0.2. That gives you 1.6 kilo. So far, see, it's fairly easy once you get to that point that we found that our RS is 1.6. But there's only one thing that we didn't do yet is to confirm that it is actually in saturation. Is it in saturation? Because we're assuming saturation. How do we know? Well, if it's in saturation, our VDS has to be larger than VOV. Now, how much VDS? Well, VDS is equal to VD minus VS. And VD is 0.2 minus VS is minus 0.68. So it's equal to 0.88 volts. But our VOV equal to 0.18, right? So as you can see, it is confirmed that our it is in saturation. So it is in saturation. We have basically concluded that is correct. So that's this one simple problem. So now let's get into our next example, which is 5.4. This 5.4 is a very interesting. It's very interesting circuit. It got this drain connected to the gate. So as you can see here, we have the circuit that's given. The problem asks you to find out what's the relation between I and V. And V is between, basically, V is equal to VDS. So V is equal to VDS. Now, the first step to look at this problem is which operation mode. Now, we know that VG is connect to VD. So whatever connect to VD is positive, and so VD this MOSFET is got to be conducting. Okay, that's the first thing. Now, of course, if you still doubt, you can always find out, VGS, right? So VGS is VG minus VS, and because it is equal to VDS, right? So because VGS is equal to VDS, this next step we're going to look at that VOV, whether VDS is larger than VOV. Okay, so what we're going to do is we're going to find out. So VDS is larger than VOV, but then VOV is equal to VGS minus VTN. But what is VGS? Well, in this case, VG and VDS connect together. So VGS is equal to VDS. So therefore, VDS got to be larger than VOV because it's larger than VGS minus VTN. So VTN is a number, right? And VDS is equal to VGS, so VDS must equal larger than VGS minus VTN. So this guarantees that this thing is in saturation mode. And this is used very often in the future that we connect this into basically guaranteed saturation operation of the circuit. So now let's go ahead and solve the problem, because this thing is in saturation mode. We basically can write down that saturation mode equation. Actually, this is already given, so basically I can write it here. So ID is 1/2 K N prime W over L times VOV squared. VOV basically is VGS minus VTN squared. Well, VGS is equal to VDS and equal to V, right? So we simply plug in this V, we'll get VD is equal to 1/2 Kn prime W over L times V minus VTN squared. And further, in the book, you know that this Kn prime can be replaced by Kn equal to this. So therefore, this ID will equal to 1/2 Kn times V minus VTN squared. So this is a very simple relationship between V and ID. I mean, that's what this problem is asking for. So we found that solution. Again, the most important aspect is that when the drain of a MOSFET is connected to the gate of a MOSFET, it guarantees that this circuit is in saturation mode. So we already verified that. Okay, so we're going to go to our next equation, exercise 5.9. If you look at it, this circuit is it's identical to the previous example, except that we now connected a voltage source and a resistor at the drain. So we know that VDS, VDS is guaranteed larger than VGS minus VTN because VDS is equal to VGS. So it is in saturation. So we still write down that. So once we write down that, we can write down the equations of ID equal to 1/2 K N prime times WL times VGS, which is same as VDS, which is in this case is VD minus VTN. So I can write one more step just in case that anybody gets confused. So VGS minus VTN squared. Now, because VGS equal to VDS equal to VD, because VS is grounded, therefore ID is equal to 1/2 Kn prime WOL VD minus VTN squared. So we got that equation. Now, in this equation, a couple parameters given. Kn is given, WOL is given, VD is given also. So therefore, we can say it's 1/2 times Kn a prime is 0.4 times WOL is 0.72 over 0.18, which is also 4. And VD is given 0.7 minus VTN is given 0.5 squared. So let's see how much we find ID, which is 1/2 times 0.4 times 0.4 times 0.2 squared. Oh, that's a long number. Let me get it, 0.02. Okay, let's see how much that is going to give us. So 0.4 times 0.4 divided by 2. Zero 0.2 squared. That gives you 0.0032. See this, make sure this number is correct. Zero 0.032 milliamps, which gives you 0. I want to convert it into microamps, so it's going to be 32 microamps. So that's our ID. So once we find our ID, we can now go ahead and find RS, find our R. So our R is equal to 1.8 minus VD divided by our ID. So 1.8 minus VD is 0.7, so that's 1.1 divided by 32 microamps. That gives you roughly 34.4 kilo ohms. All right. So, oh, that's why there's a mistake here. Sorry about that. So this is not 0.4. The ratio between W and L is actually times 4. Yes. So I want to mark down you guys rewrite this equation. So that's 4. So that's why it's 0.032, not 0.0032. Okay. So now we have found the resistance R. We have resolved that equation. If you change the R, the ID apparently is changed. For example, if we change R to say 10 kilo, what happens? Now we know that at this time VD is 1.8 minus R times ID, but we don't know ID because R change, the ID is going to change, right? So, but we know that this thing is still going to be in saturation mode. So therefore, we can find that ID is not changed. So ID has nothing to do if it's in saturation mode. So it's going to be same as 32 microamps. So therefore, we can find VD equal to 1.8 minus 10 kilo ohms times 32 micro, and that gives you 32, 320, 0.32, yeah, 0.32. So it gives you about 1.48 volts. So if we change R to 10 kilo ohms, apparently VD is going to change, and the VD actually increased quite a bit because the resistance drop on the voltage drop on the resistance is much smaller now. Of course, if you further increase R, VD is going to further reduce. But at some point, we have to maintain that VGS, which right now is VGS, is same as VDS, right? It has to be larger than VTN in order to make sure that this thing is in saturation mode. If VDS is less than VTN, it's no longer going to be in saturation mode. So this has to be larger than 0.5. So if we further increase R, then VD might drop to the point that this thing is not going to work in the saturation region. Actually, it's not going to conduct. Okay, so let's move on to our next one. So the solutions given here for you guys' convenience. Now we're going to do exercise 510. So exercise 510 is the same circuit. The right half circuit is the same as in exercise 5.9. What's the difference? That they add another circuit on the left hand, and in the future you will learn that this is called a current mirror. But we're going to explain why it's called current mirror. In other classes, of course, you'll take it, but today I will explain very briefly. So this question says, well, if we connect a Q2, which sometimes they call this a matched resistance, a matched transistors. So Q1 and Q2 are matched. Matched means they are exactly the same. Okay, exactly the same, which means their VT is the same, VT is the same, their K, N prime, W, and L, same. So from the current equation, I'm most interested in the saturation region. So in the saturation region, we know that the equation is VGS minus VTN squared. Now you know that for these two transistors, the VTN is the same, the KWOL is the same. If you look at the circuit carefully, you would find out that the VGS2 and VGS1 are the same. Why? Because their gate is connected together. The gate is connected. Gate is connected together. So they share the gate. And they also share the ground. So therefore, VGS1, VGS2 are the same. Your VGS1 and VGS2 are the same, which means ID1 and ID2 are going to be the same. So that's why it's called current mirror, because ID2 exactly mirrors ID1. So we call it current mirror because ID2 mirrors ID1. So that's why we call it current mirror. So that's quite important. But the problem itself is going to ask you at what condition would this circuit operating at the edge of saturation, between saturation and triode. So if we want to do that, we need to find out what is, because VD1, we know that's guaranteed in the saturation region already, of course, as long as VD S1 is larger than VTN. Now, we don't know VD1, of course, and VT2. We know VD1. That was calculated from our previous example. We can go back to find out that VD is given as 0.7, right? So VD1 is given as 0.7, which means VGS is given at 0.7. VGS 0.7. So for Q2 at edge between triode and let me move that away. And between saturation and triode, we know that we have to have VDS which now VDS2 has to be large or equal. Actually, in this case, it's going to be the same as so VDS has to be same as VOV, which is equal to VGS minus VTN. But of course, this is all for 2, but for transistor 2, VGS and VDS are no longer the same, but for Q1, it's the same, VDS, VGS same because gate is connected to drain. But for Q2, drain and gate is not connected. So if you mark that on VDS2 and VGS2, so we'll find out that so VGS2 is going to be same as 0.7 minus 0.5. That gives you 0.2 volts. So which means VDS2 has to be larger than 0.2. So if VDS has to be larger than 0.2, which means our I2 and I2 also given at what is I2? So I2 is given at also 2. I was given at, we found out, 32 microns. Okay, so ID is 32 microns. Therefore, our R2 is going to be equal to VDD minus VD2 or VDS2 S0 something divided by I. So it's going to be 1.8 minus 2 divided by 32 microamps. See how much that give you. 32 gives you 50 kiloohms. So that gives you 50 kiloohms. So what it says that R can be as much as 50 kiloohms. It will maintain that circuit into saturation region. If that changes, actually it's going to change. So if you increase further, this thing is going to drop too much voltage, and VDS is going to be too small. It's not going to be in saturation. So basically, what we are saying, R2 has to be less than 50K in order to for Q2 in saturation, and 50K is H. That solution. And now we're going to move on to our next example. Is 5.5, and this example is also interesting because what they're doing is they connect VG connect gate to VDD. So if you look at the circuit, so VDD is given 2 volts. VD is also given 0.1. And also the parameters VTN 0.5 is given, and K N is given at 2 milliampere per volt squared. So now we can find VGS. So because VGS equal to VG minus VS, and over here you see VG is connected to VDD, and VS is connected to 0. So VGS is 2 volts. So VGS 2 volts is larger than VTN, which is 0.5 volts, right? So therefore, it's conducting. But we don't know whether it's in saturation, whether it's in charge. So we need further to do. Now, we know VDS is VD minus VS, which is 0.1 volt. And the VOV is equal to VGS minus VTN. And VGS, we found already 2 volts, VGS 2 volts, and VTN 0.5. So we have 1.5 volts. So therefore, VDS is actually less than VOV. So therefore, it's in tri mode. Yeah, so that's why it's simple. It's in tri mode. If it's in tri mode, we want to find we can find the current. So ID is going to be K and VGS minus VTN times VDS minus 1/2 VDS squared. Now, here I use Kn because we know Kn is equal to Kn prime times WOL. So this is the equation that we typically use. So now Kn is given at 2, then times VGS is 2, or VTN is 0.5. So that's really just 1.5 times VDS is 0.1 minus 1/2 0.1 squared. How much is that it's going to give you? And our emulation 1.5, 0.15 minus 0.5, so times 2, that gives you 0.29 milliamps. So ID is 0.29 milliamps. ID now is given, so we now can find RD. RD is VDD minus VD over ID, and VDD is 2 volts minus VD is 0.1, so it's 1.9 divided by 0.29. It gives you roughly so the resistance RD was resolved to be 6.55 kilo ohms. The question also asks you to find out what is the equivalent resistance of the MOSFET, because the total, which basically what they're asking is that you have this circuit. I want to redraw it here. Now you have ID. Here is your VD. So basically, we found the current, ID, and RD, and so on, right? So if this is D, if you use, I'll use equivalent resistance to VDD over ID. That is VDD is 2 divided by 29 micro. So 2 volts divided by 29 micro amps, that gives you certain voltage, certain resistance. And if I use REQ minus RD, I got this resistance, which is equal to the resistance. In other words, you can also use RD equal to VD over ID. That's the voltage. We know that voltage divided by current, that gives you resistance, 29 microamps. That gives you 345 ohms. So that's 345 ohms. So that's the resistance. So this RD is like remember, there's no current, so don't connect this to here, okay? That's the equivalent circuit that we have. So that's for this example. Now I think what I want you to do is I want to go with even more exercises, so you guys get a better understanding of how we're going to do the problem. So we can get back into exercise 5.11. Okay. So 5.11 basically talks about the same circuit we just did, but it's going to look at what happens if we double. So if RD doubles. So which means we saw for RD initially was 6.55. So now RD is double, means 2.655. It gives 13.1 kilo ohms. So let's redraw the circuit so that we get a better understanding. So the circuit, so now we have 13.1 kilo ohms, and we still have that 2 volts at the top and the ground at S, and we have the drain. So apparently, when you double the resistance, the current and the voltage at VD, they are both going to change, right? Because when you double the resistance, the VD is no longer going to be that much. But we don't know how much exactly the current is going to be, and the voltage VD is going to be. However, one thing is clear from the previous example, that this thing is going to be in trial mode. Why? Because VGS is 2 volts, and VDS, it got to be less than 2. I mean, it got to be less than 2 volts. So unless there's zero current, if there's zero current, it's going to be 2 volts. But if there's any current, because VDS equal to VDD minus ID times RD, so it has to be less than 2 volts. So if VDS is less than 2, and VOV is going to be VGS minus VTN, and VGS is 2, VTN 0.5, 1.5. So we cannot for sure, of course, at this moment, to say that it is in tri mode. Possibly that we have to do some assumptions. So what I'm going to do is I'm going to assume it's in saturation and see what happens, because we cannot compare. There's no way we can compare these two. So I'm going to assume it's in saturation. If it's in saturation, I can easily calculate ID going to be 1/2 kWL times VOV squared, which is going to be 1/2 times 2 milli, this K prime, times VOV is going to be 1.5. Yeah, VOV is 1.5. So this is going to be 2.25 milliamps. So it's a very large current. Is it possible? Well, we will find out, because NVD will be 2 volts minus 13.1 K times 2.25 milliamps. That's less than 0. So impossible. So it's impossible because VD now becomes negative. So therefore, we can say that it is in trial mode. So if it is in trial mode, we have to rewrite the expression for ID, which is going to be KNWOL. Again, this is VGS. So VGS is, we're going to just write this down for our. Okay, so it's going to be same as, so it's 2 times inside this 1.5, VGS minus VTN is 1.5 times VDS minus 1/2 VDS squared. We got this expression. We can expand this expression to, let me copy this down to the next slide. So I can rewrite ID equal to 2 times 1.5 VDS minus 1/2 VDS squared. We can further expand this to ID equal to 3 times VDS minus VDS squared. Okay, so we can rewrite this as VDS squared minus 3 times VDS plus ID equal to 0. Okay. And so we now have VDS is a variable and ID is also variable. But from the circuit, original circuit, the VDS is the same as VD, okay? So just make sure that you guys understand. So from the circuit, we know that if we know ID, we can easily find VD is going to be VDD minus ID times RD. And RD is given, VD is given, so we have this VDD is 2 volts minus RD is 13.1 times ID. If we use milliamps, kilo ohms, the units are going to be consistent. So we can here, let's eliminate that VD squared minus 3 times VD plus ID equal to 0. So that's the equation over here has 2 variables. And then we have another equation says VD equal to 2 minus 13.1 times ID. That's the second equation, also has 2 variables. We can plug in ID to this equation to find out VD, or we can plug in VD to find ID. So either way, the final expression for this one, if we are plugging ID, which from this one you have ID equal to 2 minus VD divided by 13.1. So that's the expression that I can plug in. And I plug in this one back to here. I get VD squared minus 3 times VD plus 2 minus VD divided by 13.1 equal to 0. I combine this, I have VD squared minus 3.076 VD plus 0.115 equal to 0. And I have VD, use the quadratic equation, I found VD to be 0.05 volts. And you have 2 solutions. One of them is definitely not correct. And by plugging VD 0.5, we know that this is going to be in trial, right? Because VD now is less than 1.5. So it's less than 1.5 volts. Will we? So now we can plug it back in to find ID. VDD minus VD over ID, which is 2 minus 0.05 divided by ID is, divided by RD, divided by RD. ID is 13.1, so the ID is almost 0.15 milliamps. So we got that answer. Got that answer to make sure the answer is correct. 0.05 volts. Yeah, and the current is 0.5 milliamps, which is correct. So we got the correct answer. Let me move on to get into another example. This is going to be problem 5.83. Prepared here. So this one says I'm just going to read the problem. There's this is a MOS. The drains connect to 1 volt through RD, and the source connect to -1 through RS, and the gate is grounded. So simply, we're gonna find out VD and VS later, and we're gonna find we want to find RD and also RS. The given conditions are that current ID is given 0.1 milliamps, and VD is given also. VD is 0.2 volts, and VT is given 0.2 volts, and that K and prime is given at 400 or 0.4 milli, and L and W, L is 0.5, is 4 micro over 0.5 micro, it's going to be 8, okay? Those meters. Milliamp per volt squared, volts. Okay. So now we know that VD is given and ID is given, so we can easily find RD, which is VDD minus VD over ID. In this case, 1 minus 0.2 divided by 0.2, so it gives you 4. So, or 0.1, so ID is 0.1. So it's giving you 4 kilo ohms, okay? So ID is 4 kilo ohms. So ID can be found. But there's a current, so it's not in cutoff. We need to decide whether it's in saturation or triode. So to do that, we're going to assume in saturation, and then we can go ahead to solve the equation. There are a couple of things that you can do. Sometimes, especially you guys just get started with a problem, it's very hard to determine whether it's in saturation or whether in triode. What we can do is again, let's assume it's in saturation. So we're gonna do the problem and then we find out whether our assumption is correct. So in saturation mode, and therefore we can write our ID equal to 1/2 K and prime W L V squared. And our ID is given at 0.1, 1/2 times Kn was 0.4, WOL is 8 times VOV squared, so we can find our VOV equal to, so let's see, so we can have, so this 2, so given 0.2, so 2, so 16, so VOV is 116 square root, 116 square root 1/4, right? So it's 0.25. So, okay, so good. The VOV is 0.25 volts, and VOV equal to VGS minus VTN, and VTN is given as 0.2. So 0.25 minus 0.2 gives you 0.05 volts. So VOV is, no, I'm sorry, can't do that. So VOV is VGS minus VTN. So VGS equal to VOV plus VTN. VOV is 0.25 plus VTN is 0.2, so that gives you 0.45 volts. And VGS equal to VG minus VS, and VG 0, so that is 0.45, so we can conclude that VS is minus 0.45 volts. So if VS is minus 45, just make sure that they don't. So if VS is minus 0.45, we can find out what is the resistance RS, because if you use VS minus VSS divided by ID, that gives you RS, right? So we find RS equal to, so 0.45 minus minus 1. So here is minus 1. Oops. Minus 1 divided by 0.1 gives you 0.45 plus 1 divided by 0.1. That gives you 5.5 kiloohms. So we found RS. So far we have found the solutions, but actually there's one thing that we need to be careful is that we are assuming the saturation. So now we need to find out whether it is in saturation, because if it is not in saturation, we were wrong. So we have to go back. So how do we find whether it's in saturation? I want to recall, guys, right on the top right corner, is that VDS has to be larger than VOV. And in this example, how much VDS? So, and we're going to write down at the bottom here. So VDS in this case is VD minus VS equal to VD is 0.2 minus VS is minus 0.6, 0.45. So that gives you 0.65 volts. And how much is VOV? Well, we find out VOV is 0.25. So VDS is larger than VOV, so in saturation. So we have confirmed that our assumption is correct. So by this point, if you find that your solution didn't guarantee it is in the saturation mode, you would have to go back to redo the problem to make sure it is in the saturation mode, or it's in the tight mode. You have to redo. So this, I think we still have some time. Maybe let me go through. Just let me see. What do we have? Yeah. So let's go ahead and do a couple more problems. Now let's look at problem 5.53, and this is a simple MOSFET. We have input connected. We have the source grounded, gate, and we have R connected, and we have VDD connected. So the condition given was that VT, oh, by the way, I want to make sure the solution that was posted was wrong because VT 0.2, not 0.5. I think in the book, the solution is 0.5. That was the final step was wrong. So you guys pay attention to that. So in this example, VT 0.4, Kn prime is 0.5. Milliampere per volt squared, and lamp is 0, which means the channel effect is neglected. We want to find W over L, the ratio. How much is that? And we said that for forward condition, well, we have to give that VT or VI in this case, input is equal to VDD to 1.3 volts. For this condition, and also this says RDS is 50 ohms, and VO equal to 50 millivolts. A lot of conditions were given, and we need to find out. So VO is right under the resistance. The resistance, we also need to find it because the resistance was not given. Okay, so here VO is given. So VO is equal to VDS. Okay. And VI is given to be 1.3 volts. And VGS equal to VG minus VS equal to VI minus VS equal to 1.3 volts. So it's 1.3 volts. Maybe that's not very good. Let me rewrite it. So VGS is to 1.3 minus 0 equal to 1.3 volts. So VGS 1.3. And so VGS 1.3 is larger than VTN, which is 0.4. So it is going to be conducting. But we don't know whether it's in saturation or tried yet. So now next step is that, so VO is given 50 millivolts. It's going to be 0.05 volt. So now we can find VDS. So VDS equal to VO, right? So that's 0.05 millivolts, 0.05 volts. That is less than VOV. Are you sure? Well, because VOV is equal to VGS minus VTN, which is equal to 1.3 minus VTN 0.4. It's going to be 0.9 volts. So it is in triode. So that is conformed. If VDS is in triode, we have the expression of ID equal to 1/2 K WOL VGS minus VTN, VDS minus 1/2 VDS squared. So over here, we have 1/2 K is given. K is given at 0.4. So we can write ID. And VGS is 1.3 minus VTN 0.4 times VDS. VDS is same as VO, which is 0.05 minus 1/2 times 0.05 squared. So you have this value. So basically, except for WOL, the right hand is given. The next step is we need to find VD. So we need to find ID, but ID can be written as VDD minus VO over R. But when we introduce this R, apparently we introduce another variable, which is R, so we can still not solve it. But remember, what was given in the problem is that RDS is given 50 ohms. So basically, over here, you can simply replace this with 50 ohm resistor and to find out what is the current, because the current ID is going to be VDS divided by RDS. And this is going to be 0.05 divided by 50, divided by 50 ohm, 50, so it's going to be 1 milliamps. So basically, we're going to rewrite this equation. So you can write this back. We can always rewrite this back, like ID equal to 1 milliamps equal to let me see. Oh no, actually, guys, there was a mistake. Why would I add this 1/2 here? Remember, there's no 1/2. Okay, so it's fine. We have to be very, very careful. So ID now is 1 milliamp. So we can say this is K N W O L. This 1.3 minus 0.4 times VDS is 0.05 minus 1/2 0.05 squared. And so from here, we can find WOL. I'm not going to go to numerics anymore. So you guys can go ahead and use your calculator to find what WOL is, because 1 milliamp is already found on the left hand. But what I want to do is go back to the equation to ID. So ID equal to VDD minus VO divided by RD, or this over here actually it's just called R, no D. So okay. All right. So we have R equal to VDD minus VO divided by ID. And VDD is 1.3 minus 0.05 divided by 1 milli amps. So you can get the solutions of that. And this was a little easier to get. So as you can see from this a couple of examples, that in many of the problems, what they wanted you to find out. So often, they want you to find out the resistance, or find the current, or find the voltage output, and so on. So this is a very typical problem that is given. Let me just make sure that we have this. Okay, we got. I wanted to get the numerical values for you guys so that you guys don't see. So, okay. So because here is really 1.25. So this 1.25 kilo ohms. So this is a very easy one. In fact, I should have done it. So 1.25 kilo ohms. And for that W/L ratio, we find to be 14.4 by just doing those examples. So I will stop here because we have a couple examples already. And in next lecture, we're going to continue with more examples, more difficult examples, and more like variations of different examples, so that we can get you guys really familiar